Hello guys, I have here a problem that the setup is balls into beans. So I have m balls that are going into k beans, right? They are independently thrown, just like we talked about balls into beans, and uniformly each ball can equally go into any of the beans. But I'm not asking the combinatorial question. I'm not asking how many ways can those balls end up as counts into beans like we did in the module 5. I'm asking a statistical question. I'm asking what is the expected number of balls that fall into a bean and what is the expected number of empty beans. Like at the end of throwing those m balls, I want to know on average how many balls am I going to have per bean, and on average how many beans are going to be empty. So how do we solve this problem? We solve it, of course, with random variables. So let's proceed. Part 1. Let's say we define the random xij. This is a double index random variable. Is ball I goes into bin j 1 if that happens. So let me move this stuff a little bit. So 1 if, 0 if not, right? So this is a random variable that depends on a ball and on a bean. So we have total m times k random variables, right? There's a random variable for every pair ball bean. So now we can say, okay, let's take this question 1. So expected number of balls in, say, any bin. Pick a bin, bin 1. It will be the same. It will be bin k in general. No, the k is the total number of bins. Say bin t. It's the same for pick a t. 1 smaller than t smaller than k. It's any bin. Could be bin 1, bin 2, bin 3. It doesn't matter. It's the same average. So this will be expected of, if you think about in terms of these xij variables, this is the sum for all the balls. So from I equal 1 to n or m, we say, of this xit, right? Let me put this square bracket here, right? So this is let's write it down in words. Is it counts as 1 for every ball that goes into that bin t. Again, t is a fixed number here. It could be 1, 2, 3 up to k. So because of the linearity of expectation, this is a sum for I equal 1 to m of expected value of xit. This is easy to compute, right? Expected value of xit, it's simply 1 times the probability of xit equal 1 plus 0 times probability of xit equals 0. So that is simply the probability of xit equal 1, which is the probability of ball I going to bin t that is uniform, right? So it's 1 over k because that ball I has an equal chance of going to all the beans. So it's 1 over k. There are k beans, uniform over k beans. So it's 1 over k. So then what we have here, right, it's simply, I'm going back to this equation, it's m times 1 over k. So that's intuitively very easy to swallow, so to speak. If you throw m balls on k bins, on average, you get m divided by k per bin. But now you have a mathematical result showing you that that's actually true. So what about the second part? Part 2. What is the expected number of empty bins? Well, we have to see what is the probability that a bin remains empty. So we fix a bin, call it t, like before. So that's 1 smaller than t smaller than k, and then let's say yt, it's a random variable, is 1 if all balls miss bin t, and 0, that means, of course, that's empty, right? 0 if not, which means not empty. So we want to calculate the probability of this yt equal 1. What is the probability that all those balls missed the bin t? Well, that is, we have, let me explain why. We have m throws, and they all independent. So this is the product from I equal 1 to n of ball I probability. Ball I misses bin t. So that we're going back to the first part. That is the product from I equal 1 to n. From I equal 1 to n of probability. I'm looking back at this definition here, who is xi. That is the probability that xit equals 0, right? Again, that's what it means to miss the bin t. It means it went somewhere else. It went into the nut, right? So notice I put a t. That's a j because I'm talking about bin t here. That's a bin j in general. So in here, what is the probability? Let's calculate this thing. We're getting a product from I equal 1 to n of that probability is, I think, 1 to m. There are m balls, sorry, m. So we getting 1 minus 1 over k, right? Because probability to get to bin t is 1 over k, but we want to avoid bin t, so it's 1 minus that. And of course this product then will be 1 minus 1 over k, at the power m. So now finally the expected number of empty bins, it's the expected number of the sum over all those bins, t equal 1 to k, of this y yt. So that will be, by linearity of expectation again, that is the sum from t equal 1 to k of this expected value of yt. So that is k times times 1 minus k at m. 1 minus 1 over k at m. This can be approximated if you know the Euler's number. This is approximatively k times e at minus m by k. That's not important from statistics. That has to do with the limit of 1 minus 1 over k at k. But the statistics part is to figure out the answer, not necessarily the approximation. So we can calculate or approximate the number of empty bins if we to throw m balls into k bins. Finally, I have one more point of this problem, which is a little bit more advanced. So I would say this is optional. This is called the coupon collector problem. That has a name. The same setup. We're throwing the same. We have k bins. So let me drop them here. This is bin 1, bin 2, bin 3. At some point we have bin, that bin that we talked about, bin t. Then of course we're gonna have bin t plus 1, and then we have bin, the last one, which is bin k. And we're throwing those balls in. I wanna draw this. The question says m here is a random variable. It's not fixed, so we don't have m balls this time. We have here, we throw enough balls until we don't have any empty bin, right? So in here, m is a random variable. That is because maybe today, if I am to fill k bins, I need 100 balls, but maybe tomorrow the same k bins, if I start filling them, I need a different number of balls, right? Every time I start filling k bins, I'm not sure how many balls I'm gonna need until there is not a single one empty. So this is the, I draw them in here. The bins are now in not empty order, or for that problem, that will be the coupon collected order. In other words, the first bin, the first ball goes in here for sure. So first ball goes to bin 1. The next bin that gets its first ball, let me actually write this down, that'll be easier to follow. Is bin 2. So that means the first ball maybe went here. Here it is, that's the first one. But maybe there were some other balls that went here. It's possible that the next two balls, this is ball 1, but then I got a bunch of balls that all fill in bin 1. I'm not sure. But in here, it's the next ball, that's the next coupon. Because we don't care about the coupons that get the same bin. That will be the same coupon collected a number of times, but we care about collecting different coupons. So in terms of balls into bins, the next bin is bin 2, and then again there might be some balls that fall in here and more balls that fall in the first one, but then the next empty bin that gets hit is bin, let's call them big bins, bin 3. So that is this one, and then the next is bin 4, so on and so forth. So the way this process goes again is that at any point in time, so I'll be here at bin T, this bin. Before moving to bin T plus 1, there would be a bunch of balls that keep falling into these existing bins, and I don't care about them. They don't advance at all because I'm putting balls into the same bins that I already have balls in. I care about when a ball falls into a next empty bin, which will be the next bin right here. So what we want to do is, in order to calculate, of course this will be the total number of bins. All these bins here all the way down will be the total number, that's M. What we want to calculate is the expected, so this will be right here, number of balls going to bin 1, all of them. Then this is number of balls until we hit bin 3, the next one, right? So we kind of break them into chunks of balls. This is how many balls until we hit bin 4. It only counts the first ball. We only look at the first time we hit a bin, because after that we just increased to one more bin, right? So this will be here the number of balls until we hit the first time bin T, and then number of balls until we hit bin T plus 1. So what happens here, we're gonna call these variables x1, x2, x3, and so on and so forth until xt plus 1 here, xt. So xi, xt is the number of balls after hitting bin T first time until we hit bin T plus 1 first time. So it's like, how many extra balls do I need until we hit the next empty bin? The probability of any ball to hit bin t plus 1 is well, 1 minus the probability that this ball X falls into one of the non-empty T bins right now, right? Because I'm at the point where I have balls in every one of these bins, and as long as I put balls in those, I'm not advancing, I'm not filling a new bin. But as soon as I hit this one for the first time, that's an advance. So probability of this, it's exactly, of course, I have 1 minus, I have T bins already non-empty, divide by how many bins are in there, because it's a uniform probability. So because that is the chance of success, we call it chance of success. And it's fixed. Until I move to the next bin, I'll always have this probability with every ball. As long as the balls, again, as long as the balls fall into these first T bins that have already balls in them, I'm not moving forward, so I have the same chance of success. The next bin will also fall into one of those. So that I'm going to skip this detail for now. That's an exercise. This is a geometric distribution. So this xt will be so the expected value of xt, it'd be the expected of x, which has a geometric distribution with success equal 1 minus t divided by k. That we know how to calculate. We can also do it with series. I'm going to skip it for now, but we can do it with a series. The expectation of such a distribution is 1 over the success rate. That's very easy to show. It's the sum that goes x plus x squared plus x cubed plus x fourth plus so on and so forth is equal with 1 over 1 minus x. Right? If x is any number between 0 and 1. So we're using that formula because it's a geometric distribution. I think we need a 1 here too. 1 plus. So the success rate is that will be k. Sorry, so that is 1 divided by 1 minus t by k. So that will be k divided by k minus t. Now the total number of balls is the sum of this xt, because it's you know, it's, think about it, is the number of balls till bin 1 plus the number of balls till bin 2 plus the number of balls till bin k. So it's a sum from t equal, I think it's 1 plus, because the first one it's a 1, right? Certainly the first ball goes to the first bin. T equal 1 to k of this, so that is sum from t equal 1 to k of k divided by k minus t, plus 1. I guess I'm missing a 1 here somewhere. So that would be k times the sum of t equal 1 to k of k minus t plus 1, which is roughly, this is the same as, looking at it backwards, is the sum from t equal 1 to k, that's 1 here, of 1 over t, right? So that is the harmonic number. So that is roughly k times hk. The harmonic number is 1 plus 1 over 2 plus 1 over 3 plus 1 over k. So that shows this problem of how many balls do I need to throw on average until all the bins are non-empty. Make sure you understand that that's a different problem than the second one here, which is what is the expected number of empty bins. You gotta make sure you're not confusing those two. After I throw n balls, I can have some empty bins. On average, I'm computing that in part 2. The other one, which is kind of the dual problem, is if I don't want to have empty bins, how many balls do I need to throw? What's the average? So that is the average number right here.